Hi guys, and welcome to our Wadix Technologies YouTube channel. Wadix Technologies is a company specialized on embedded systems training and online coursing. We offer a big variety of free online courses specialized on embedded systems technologies. All of this is within our YouTube channel. We provide as well blogs, articles, advanced online courses, and one-to-one training services specialized on embedded systems technologies within our website www.wadixtech.com. So don't forget to hit the subscribe button of our YouTube channel, as well as checking out the different services we offer within our website wadixtech.com. Hi guys, and welcome to today's video course. In today's course, we're gonna see the GNU Make build tool, as well as the ability to use the Makefile as a build system. First of all, we're gonna discuss the added value of a GNU-based Makefile project and the different use cases of those Makefiles. We'll see as well the main features supported by the Make build command tool itself, as well as the main characteristics and aspects of this Make tool, like parallelism, recursion, and inclusion. We're gonna see as well how we can use the Makefile and deploy it for our embedded systems based projects. And of course, we will see the main and basic syntax used within a Makefile. And finally, we'll be able to write our first Makefile for our embedded systems based project. Now, the first question anybody will ask is, what will be the added value of using our Makefile within an embedded system project? Within an embedded system project, we'll have big number of sources and headers that they need to be pre-processed, then compiled one by one, then link it to generate a single image that will be loaded within our embedded device. Now, the different sources will need to be processed, if we'll do it manually, of course, one by one, then compile it one by one, then link it all together to generate our final executable and linkable file. Biggest the project, biggest the pain that we need to go through to process and compile those sources one by one. Hence, there is a need to automate this whole flow of processing our embedded system based sources. And this is the main role of our Makefile. Makefile allow writing certain rules to automate the flow of pre-processing, compiling, linking, as well as creating directories for our embedded system based project. Hence, we can encapsulate all those steps within a single Makefile. So we start by our embedded system source files, and we will end up by a single image to be loaded into our embedded device. And the whole steps, as you can see, will be abstracted and embedded within our Makefile file. Before tackling the different features supported by our Make build tool, you will need to distinguish between the Makefile and the Make build tool itself. The Makefile is just the file that will embed the syntax and set of rules to automate the flow of compilation and building of our embedded system project. However, the Make build tool is the tool itself that will be able to parse this file and execute those rules. Now, in terms of features, the Make build tool itself, which will be this one, can support incremental build. Means if we initiate a first build that doesn't finish or even finish, and then we need to trigger a second build without really cleaning up the previous build, then the second build will be able to detect any modification that happen on our sources. And hence, we don't need to build the whole project from scratch. Actually, we'll build and compile only the modified files. This leads us to the second point, which is that the Make has the ability to scan and detect changes and modifications that happens on our sources. And hence, once we try to build a second time our project, we'll end up by having an incremental build. Means we'll compile and build only the modified and changed files. The Makefile does support recursion. Means we can include a Makefile within another. Then we'll have the ability to use and import the different environment variables within our Makefile. Also, the Make build command does support parallelism. It means we can have the whole processes that are needed to parse and execute the different rules run in parallel way. So instead of having single thread or process, we'll have multiple processes to achieve the goal of executing and parsing the different Makefile rules. And finally, the Make and Makefile provide to us low-level control over the different rules and dependencies. This is not possible with other sophisticated build systems like CMake. Now, let's start to cover those features supported by our Make build tool and the Makefile one by one. As we have seen in the previous slide, one of the major features supported by our Make build tool will be the parallelism aspect. Means the Make build tool, once parsing our Makefile that contains the different rules to automate the flow of execution and compilation of our embedded system project, it will try to split out the different rules into dependent and independent scenarios. The main goal of this is that we can isolate, let's say, the rules and jobs that doesn't depend on other rules. And this one can execute then in parallel with the other ones. So instead of executing sequentially the different Makefile rules one by one, we'll be able actually to isolate the ones that doesn't depend or has any dependencies to the rest of the rules, and then trigger a parallel build. This will have significant impacts on terms of performance. Hence, we'll be able to reduce the build time of our project. Now, another characteristic and aspects supported by our Make build tool is the recursion. Recursion means the ability to trigger the execution of another Make commands within a top level one. This is an example of a project that consists of top-level Makefile, then 2 submodules. Each of those submodules will have its own Makefile as well. Here we can execute the submodules separately, means we can invoke the make command first of all for the module number 1 to parse and run this Makefile, and then we invoke for the second time another make command to execute and run this Makefile dedicated for the module number 2. However, we can automate the triggering of the execution of those 2 Makefiles by creating a top-level Makefile, and this one will invoke first of all make command for the module number 1. So we'll need to specify that our Makefile to be parsed and executed will be the Makefile of our module number 1. Then we can add a second line within the same Makefile to invoke the module number 2 Makefile. Same here, make then minus Makefile, and then equal, and this time this will be our second Makefile. Inclusion, on the other hand, which is as well another characteristic and aspect of our make command, will include a Makefile based file within a top level Makefile. So this one and this one are not standalone Makefiles, means we cannot invoke them via this make command. This will not work out. However, we can embed set of rules and jobs within those .mk files. And this is needed to break down the complexity within our main or top level Makefile in smaller units. It's similar to a C or C++ based project. Instead of writing everything within a single file, just we create a project, and then within each of the files we can just put one piece of our code. Similar here, we don't write everything within a single Makefile. To make life easy, we create sub.mk files, and each of those .mk file will contain portion or small chunk of the Makefile code. And then we include later on those .mk within the main and top level Makefile. This one, of course, will be invoked via the main command. So this one will parse this file and try then to get the different rules out of it. Of course, if there are inclusion, then those inclusion will be extended and evaluated. And hence, the different rules defined here and here will be as well extracted and extended so that the make will be able to build the whole tree of dependencies across the different .mk modules. And then will trigger top level execution for all those rules. Another aspect that we need to keep in mind is that make is just a build tool. Hence, it cannot be considered by itself as build system. Build system is a system that embed beside the ability to parse and execute certain rules to compile and build our project. It allows copying, editing, removing, checking the different sources, headers, directories, and so on. So it exposes a lot of functionalities that the user needs in general in a full complete embedded system based project. Make doesn't provide this. Make provide only subset of sequences that a complete build system offer. Means the Make offer the ability to build your project via defining set of rules that will be parsed, evaluated, then executed. However, we need much more than only the build capability to start speaking about a complete build system. So always avoid this confusion and make sure to keep in mind that Make is just a build tool. It offers only the build capability. That's it. The Make build tool, as we have seen, cannot be considered as full complete build system. It is just a build tool. However, the Make as a build tool can be used with a combination of set of external tools to create a customized full complete build system. So if you combine and include the user of tools like CP for copying, RM for removing directories, set for modifying set of sources, and so on, with the build capabilities supported by our Make build tool, we can create this complete build system. And in most of the embedded system projects, this is what is happening. Means we use Makefile, we include set of rules, and those rules can make use of those external tools to do certain modification, update, copying of the different embedded system sources and headers. And hence, we'll be able to achieve the full capabilities of a complete build system. Plus, as stated before, we'll preserve this ability to have full control over the flow and the processes and the steps needed to build our embedded system image. Other abstracted build systems like CMake, although it offers all those functionalities in a cleaner way, but it automates the generation of the backend Makes and Ninja based build files, and hence you don't have that fine granularity control over what has been generated by the CMake. However, if you do write your own Make files by yourself, you will have this low-level control. This is an example on how we can use the Makefile to automate the flow of execution of the different rules and jobs to compile and generate the final embedded system based image. Here we can define set of targets. Those are considered as Makefile targets, and each of those targets will represent basically an output file. So this one, for instance, will present the output object file coming out of the compilation stage of our main.c. This one will represent the final ELF image coming out of the linking stage of the different objects of our embedded system project. And finally, this .funny target, this one will be our entry point to trigger the execution of our Makefile rules. So hence, we can invoke make all like this, and then the Makefile will just start parsing, evaluating, and running the different rules. Besides those targets, we'll need to create kind of tree of dependencies between those targets. Our entry point will be this all basically Makefile target. However, to trigger this sequence of execution of the rest of the rules, we need to create a dependencies between this rule and the other ones. Hence, for this one, it will have a dependencies to this image.elf, because this is the output file to be generated and loaded into our embedded device. Then this one will have its own rule to be able to get generated. And this rule consists of linking the different objects to generate our elf. Then those objects cannot be generated by themselves. Hence, we need to define another rule that will be able to compile the original sources and generate those objects that will be used for linking stage. And then we'll be able to have this kind of tree of dependencies between the different Makefile rules. And this is the main idea behind this Makefile. The idea is just to create a rules, then create a tree of dependencies between those rules. And then once we execute the entry point of our Makefile, it will be like a domino-based game. Means one rule will trigger another one, and the other one will trigger another one, and so on, until we finalize the execution of the different Makefile rules to achieve the generation of our final image. Now we will try to cover some main Makefile syntax within those slides. First of all, we'll start by the assignment syntax. Here, we can do kind of direct assignment of a value to a Makefile variable. So we can create variables within our Makefile, and then we can do kind of direct assignment of certain values to those variables. This is quite similar to what we have in C or C++. Then we'll have this kind of Makefile specific assignment where the value of the variable to be initialized will be expanded during this assignment. This means mainly is that if we include another defined variable within the assignment of this bar1, then this variable will be expanded during the assignment. Hence, in background, the bar will get assigned this value, boo example, because this variable get expanded immediately here. So instead of assigning boo example, we can just assign $var. This is to represent the content of our var variable, and then example. So this is similar. We can overwrite an existing value of a Makefile variable again via this direct assignment. So now the content of this var Makefile variable will be test instead of boo. This one is a conditional assignment. Means it will check first of all if this var Makefile variable has been already initialized and get already assigned a value. If not, then it will get assigned this one. If yes, means this variable has been already initialized and has been assigned a value, then the assignment will not happen. And this is our case. Means the var Makefile variable has been already initialized, and hence this assignment will not happen. So as you can see, var and bar still the same. Finally, we can append a new value to an existing Makefile variable. Here we have chosen to append this word value to our existing Makefile variable bar. Now the value of bar is boo example. It will not be test example, because the expansion of this Makefile variable is done during the assignment of our bar Makefile variable. This doesn't happen here. Hence, even if we update our var Makefile variable later on, this assignment will be connected and fixed to the old content of our var Makefile variable. Here, if we are appending certain value to this bar Makefile variable, then we appending this one to this string. Hence, the end result will be boo example world. If you have been already exposed to one of the existing Makefiles, for sure you have seen one of those magic syntax within the Makefile. Those magic syntax and variables are used mainly to reference and substitute certain input parameters, prerequisites, and Makefile targets. So, if you're gonna write your Makefile rule, you need to specify a Makefile rule target and set of prerequisites for this target. Now, within the body of the Makefile rule itself, instead of calling those prerequisites per name or the target per name within the body, and this will be, by the way, quite painful, especially if you have very long list of prerequisites dedicated for this Makefile rule, we can just reference those input prerequisites as well as our Makefile rule target using set of Makefile syntax and variables. Example, this $@ can be used within our Makefile rule to reference our Makefile rule output. This one can be used to reference the first Makefile rule prerequisite. In our case, will be source.c. This one will be used to reference all Makefile rule prerequisites. In our case, will be the source.c and the source.h, as you can see. We can as well reference the target directory using @d. So D stands for directory. Means we can, out of the Makefile rule target, reference only the directory of the output file. Hence, we don't need to specify the directory plus the name of the file. Maybe for certain things we need only the directory of this output file, not the directory plus the file name. Similar here, we can just try to match the input prerequisite to the output target. This is useful mainly when we are trying to compile, or to be more precise, to automate the compilation of the different embedded system sources. So each source will have a matching object file, and this object file will have the same name as the sources. So instead of writing Makefile rules for each of those sources and objects, and ending up by having a huge list of Makefile rules, each of those rules dedicated for a single source and each matching object file, we can just write a generic Makefile rule that will be matching the name of the object with the name of the input source prerequisite. And this can be done via this percentage sign or syntax. So here we are matching the name of the output object with the name of the input source. And hence, this can be generic for all of those Makefile rules that tries to compile different sources of our embedded system project. Another powerful set of Makefile syntax are substitutions. In the first use case, we're gonna substitute any pattern that end with this .c suffix by the same pattern name but with different suffix .o. Hence, the make is gonna expand the content of this source Makefile variable, and this one does contain, as an example, list of .c files, a.c for example, foo.c, and so on. Then try to match the suffix that we want to substitute, this .c, and once found out that those files they end up with this suffix, then it's gonna substitute the suffix by .o, and the file name will be kept the same. So this will end up by foo, and this will end up by a.o. In the second use case, we're gonna try to substitute the suffix and the path, as you can see. So the make is gonna expand the content of this Makefile variable files, and this one can contain a list of files. Each one, for instance, has similar path, like source a.cafe, then source b.cafe, and similar to this, it will part this list, try to catch the different files that they end up by this suffix, and then is gonna try to keep the same name, like A, then this is P. However, it will change the cafe suffix by JSON, this .js, as well as the top level path, this one. So instead of source, will end up by leap here and leap here. So it is not only about suffix, but this can be extended to paths. Finally, we have a very powerful built-in Makefile function, which is pattern substitution. This one can take as input list of files and parameters. So this wildcard is just will extend any kind of file ending by this suffix .c. So we end up basically by having a long list of .c files. And of course, we can specify the path that this wildcard must extend this list of sources. Then it will try to catch up basically the files that they have this suffix.c, and then it will keep the same name of the files. However, it will substitute the .c suffix by the .o. As you can see, this is b.o, this is c.o, and so on. So it's quite similar to this one. However, as you can see, this is, let's say, linked and hard-coded to substitute the .c suffix by the .o. This pattern substitute can accept basically any kind of patterns to be substituted. Means it can substitute the suffix, it can as well substitute the paths, as here. It can substitute both. As well, it can accept any input or list of parameters, files, or whatsoever to try to substitute the suffix and set of patterns with the new ones. So it's quite flexible and quite powerful, and use it widely within our Makefile. We'll have as well as built-in functions within our GNU Make a set of basic Makefile filtering functions. Those ones allow the cleaning up of set of Makefile variables, as well as filtering set of patterns out of list of sources and files. In this first use case, we are cleaning up any extra white space within our string. In this example, this string underscore var consists of those list of characters. As you can see, we have an additional weight or white space here, as well as here. So strip will get rid of those extra white space, and the end up result will be a GNU Makefile variable that has been cleaned up from any additional white space. In the second use case, we're gonna use the GNU Make built-in filter function. This one will parse the content of this Makefile variable, which consists of set of files, and then try to match this pattern. Means it try to find out which file end up with this .less suffix. Once found out, then the outcome result will be only the filtered and matching basically file. In this case will be our c.less, and the other one will be thrown out from the end up or from the end result. Then we can have this filter out built-in function. This one will parse again this Makefile variable content, expand it of course to set of files. This will be the content of our files Makefile variable, but this time it will throw away this matching pattern, and the end up result will be the content of our Makefile variables, but without this pattern. So it will be the other way around from the previous use case. Here will end up by having the pattern that end up with this suffix less, and here will end up by a list without the file that has this pattern or suffix dot less. Beside of the built-in functions within our GNU Make build tool that we have seen in previous slides, the GNU Make build tool does support set of input command line options. This is an example of those command line options supported by our Make build tool. First of all, we have this -- environment override or -e. This one tells the GNU Make to prioritize the global or environment variables assignment of set of Makefile variables in respect to the local assignment. Example, if we have this compiler variable cc which get initialized globally at our system level by this value gcc, it means we're gonna use the gcc compiler. Then within our Makefile and locally we do another reassignment of this variable to be clang, means we're gonna switch to use the clang compiler without the usage of this -e. Then the GNU Make will prioritize the local assignment, and hence will end up by using this clang compiler over the GCC one. However, sometimes we want to influence the behavior of our Makefile without modifying it. Means instead of inserting a spaghetti of if-defs to tell the GNU Make to use the clang for certain conditions and then the GCC for another conditions, we keep the GNU Makefile as it is and just we redefine our Makefile variable at system level. And then we invoke the make command with the -e. Hence, the GNU Make will prioritize the global one over the local reassignment. And then the compiler variable will be fixed and assigned this GCC compiler instead of the clang. Another option is this -b or -- always make. We know that our Makefile will be expanded to set of rules that will be executed to process set of files and sources. Then after that, we can invoke another time the make command to process only the modified and changed files. This is what we call the incremental build. So instead of building our project from scratch over and over, we can invoke the first time make to build the project from scratch and process all those rules, taking care of all sources. Then for the second, third, and as many times as we want, we can invoke make again, and the make will check the timestamp associated to each file. The modified file or changed one will have an updated timestamp compared to the other ones, and hence the make will know that this file has changed in respect to the other ones, and will execute only the Makefile rule that is processing only that file, and the rest of the GNU Makefile rules which process the unmodified files will be kept the same and will not be executed. So instead of running the whole thing from scratch, we'll just run and execute the Makefile rule taking care of the modified file. This will speed up, of course, our build time. Nevertheless, sometimes we want to enforce the building of the full list of the GNU Makefile rules, and hence building kind of our project from scratch. For that, we invoke make with this option -p. Then we have this minus silent or -s. This tells the GNU Make to compile and execute the different Makefile rules to compile our sources silently. Means the Make will not print the content or the body of the different Makefile rules. Example, if our Makefile rules consist of compiling a C source to generate an object file out of it, and the body of this Makefile rule is like invoking a compiler command, let's say gcc, then take this input, then generate the output. In general, if we invoke the make command without this -s, it will print the content of this line. This will be printed in our console. However, if we have a huge project, then the console can be messy. Hence, we can invoke this -s to tell the make not to print the body of our GNU Makefile rule. Finally, we have this command -g or -jobs equal n. This tells the GNU Make to execute the different Makefile rules in parallel processing. So this n tells the GNU Make how many processes are used to execute those Makefile rules. Now this number in general must be associated with how many processors supported by our machine and how much or how many dependencies we have between the different GNU Makefile rules. So things can be a little bit complicated to determine the exact number for our parallel processing. However, in general, we can use 4 or 8 for a machine that does support 4 cores. 8 means the GNU Make will try to generate 8 jobs to execute the different GNU Make file rules. But this doesn't force or enforce the GNU Make really to generate 8. So this is the maximum number that can be generated. Whether 8 or not, really this is depend from the amount of dependencies between the different GNU Makefile rules. So if we have, let's say, low dependencies, it means a lot of those GNU Makefile rules doesn't depend each one from the other, then GNU Make can run those rules independently, and hence we can have 8 jobs used to execute in kind of parallel way those different Makefile rules. However, if we have a lot of dependencies between the different rules, then this can go down to 4, 3, 2, or even 1. So personally, I use either 4 or 8 to prioritize this parallel processing and make use basically of the different cores supported by our machine. But as I stated before, this doesn't really enforce having 4 or 8 jobs handling those rules. This depends from the load on your machine, from how many cores you have, as well from the amount of the dependencies between the different GNU Makefile rules. Now we're gonna start writing our first Makefile file. This Makefile, it will illustrate and demonstrate the different syntax and learning that we have got across the different slides and sessions. And it will allow us to compile and build our embedded system based project. First of all, you need to create your Makefile file. So you can, or you must name it as Makefile, and then you need to remove any kind of suffix here. This one is the file to be parsed by our GNU Make build tool, and it will embed the different rules, prerequisites, and functions to build our embedded system project. Here, as a proof of concept, I will create two directories. One will be my source directory. This one will contain the different .c sources, and then I will have the include directory. This one should contain the different headers of our project. I will create a single .c file. This will be our main. And then for the includes, I will create as well a single header file, helpers.h. Now here, I will need to define the different rules, prerequisites, and embed the different functions and sources needed to build our first Makefile project. Now, for our first Makefile project, we're gonna need certain prerequisites to be able to build this project. In terms of tooling, we'll need first of all the ARM non-EOB GCC, which is the GNU GCC compiler from ARM, and this is dedicated for the ARM Cortex-M microprocessors. So our project will be targeting an ARM Cortex-M3 based platform. The second prerequisite will be, of course, the GNU Make build tool itself. Beside the GNU Make build tool, we'll need, of course, set of tools and applications that allow, for instance, creating directories, removing directories, modifying files, and so on. Cygwin64 does offer those kind of applications and tools, and those one can be integrated as part of our Makefile rules. You can do the installation manually, one by one, by yourself, or you can just check out our Wadix tech repository, and to be more precise, the Wadix tools, and that one embed all the set of tools needed to build and compile our first Makefile based project. We'll need now to clone and check out our Wadix tools GitHub repository under C drive. My recommendation is to pick up C drive because it offers short paths to the different tools and applications to be used out of our tools directory. Now, in terms of tooling, our Wadix tools GitHub repository offer quite big number in terms of toolings and applications. Nevertheless, for our Makefile based project, we will need mainly the ARM GCC compiler. This is the ARM non-EOB GCC compiler from ARM, and this is targeting mainly the ARM Cortex-M microprocessors family. Our Makefile project will be an ARM Cortex-M3 based project. Then we'll need this GNU Win32. This one does contain already our GNU Make build tool. And finally, we'll need set of tools and applications to be used in combination with our Make file. So those applications will be used as part of our Makefile rules to create directories, remove directories, copy files, change or modify existing files, and so on. Segwin 64 does provide those set of applications. Example, we can create directory via this mkdir application. We can remove via rm as well as rmdir for directories, and so on. Now we'll need to set up our Windows environment variable path to point to those applications and tools. Hence, the Windows system will be able to recognize the location of those tools and applications once they get invoked via the command line. For that, I have prepared this PowerShell script install environment. Once executed from a PowerShell session, then the Windows environment variables for the current account will be updated to point to our applications and tools needed by our project. If you want to revert back, then you can use this an installation environment PowerShell script. So this to install, and this is to restore back the old paths. To execute those scripts, you need first of all to open a PowerShell session. So like this, as you can see. Then the first thing to be done within the current active PowerShell session is to enable the execution policy. This one enables PowerShell to accept external scripts and execute them. Without running this command, the PowerShell session will block the execution of our PowerShell installation script. Once we executed this set execution policy, we can navigate to our tools directory. Then we initiate the execution of our installation PowerShell script. Once done, the Windows environment variable path will be updated and pointing to our applications. So if we inspect the environment variable of our account, then we go to path. As you can see, the path has been updated to point to our Segwin 64 applications as well as Make build tool as well as the ARM GCC compiler. If you want to revert back, then you can just execute the uninstall PowerShell script. Now, if we inspect again, as you can see, the previously added tools has been removed. Now, I will just execute again this install PowerShell to be able to move forward within our Makefile based project. As you can see, this has been added again. Now we can move forward and check out our Makefile based project. Our GNU Makefile based project is an embedded system project that is targeting an ARM Cortex-M based microprocessor. The project itself is part of Wadix Technologies GitHub repositories, and this is the path to our GNU Makefile project. Now, the content of this GitHub link is a full complete GNU Makefile based project. It means kind of plug and play project. So you invoke the make and then everything will build. Nevertheless, to illustrate and demonstrate what we have learned across this course, we'll just keep the C and headers based files and we'll remove all the make files. Then we'll start coding the make files from scratch to demonstrate the different Makefile rules, implementations, and the usage of the different built-in functions. Now, this is our first Makefile-based project. This is an embedded based project that is targeting an ARM Cortex-M3 based platform. Therefore, we can add basically a set of C sources as well as set of headers. Then we need to have a linker script that is specific basically to our Cortex-M based platform. And of course, we'll need set of drivers matching basically the hardware IPs and peripherals within our embedded device. Now this is just a template project, means those functions sources are just used to prove or demonstrate basically how we can use Makefile to build the whole project. So they are irrelevant basically to our embedded device. Now the first thing to do is to create this file, Makefile. This one should not have any suffix or extension, and as you can see, it is empty. Once you start and open a command line, then you invoke the make command. The first thing this make build tool will do is parsing this Makefile, and then it does the expansion of the different Makefile rules encoded within this file. Then of course we'll start the execution of the different jobs that are executing in background those rules to build our project. Right now there is nothing to build, so the file is quite empty. So hence our make build tool will return this error. Now, before jumping into your Makefile and start coding there, you will need first of all to take one step back and then try to break down the different inputs and expected outputs out of this Makefile. This is an embedded based project, so it consists of set of C sources as well as headers and linker file. Now those ones are needed by the compiler to be able to generate the object files, then link them to generate the final binary to be loaded into our hardware. Hence, the first dependencies to our Makefile is the compiler, and to be more precise, the whole toolchain that has the compiler, the linker, and so on. The second dependency will be, of course, the list of the sources to be compiled. Third dependency will be the set of applications and tools needed, for instance, to create the build directory where we will have our objects, copy files, removing and cleaning up directories, and so on. This we will get out of Cygwin installation. And finally, we're gonna expect as output different objects files coming out of the compilation stages, as well as the final binary. Now, based on this flow of inputs and outputs, we can easily recognize that we need to create kind of Makefile variables to point to the compilers and different tools needed by our build flow. My recommendation is to split this out of the Makefile itself, hence we don't end up by a big messy Makefile that embed all those variables and custom functions. I can start by creating this tools.mk, and here I can just define basically the top level directory where all my tools are located. If you remember, this has been checked out under C drive. This means if I don't set it from the command line, it will take this default value. However, if I set it from the command line, then this assignment will not take any effect, and hence the tools will keep the previous assigned value. Now the default value to be assigned to the tools will be basically the default location of our tooling. We need, of course, the set of applications and tools to be provided by the SIGWIN to be able to create directories, remove, copy files, and so on. So I will define another variable. It's called SIGWIN64, and this one will take as value the path to the SIGWIN's application. Then SIGWIN64, then bin, and we are done. Then I will create another .mk file to embed the paths to the different locations of our compiler linkers, as well as encapsulating the different compiler flags and linker flags to be passed later on to the compiler and toolchain. Done. I open here. So our compiler will be the ARM GCC1. So first of all, I need to identify the top level directory pointing to this ARM compiler. So this will be already our tools, and then it will be under ARM GCC. Then I need the version. So what I'm gonna do is, first of all, I will create the path to my compiler. Then I create the path to my assembler and create the path to my linker. Then it will be something like this. This dollar is used to evaluate and expand the content and the value of our Makefile variables. Then this will be ARM GCC, then the version. So I will create another Makefile variable to specify the version of our ARM GCC compiler. The ARM GCC compiler that we're gonna use will be the 10.3.2. So 10.3.2, and here again I invoke this dollar to do the expansion of this compiler version. Then the toolchain itself will be located under ARM GCC, then bin, and here we go. Now the compiler and the assembler and linker for the GNU GCC based one can be all the same. So we can use the GCC actually to compile, assembler, and link. So to make life easy, I will keep the GCC as our front end tooling, basically to compile, assemble, and link. Just keep it like this. So far, so good. Now we need to define, of course, the different flags to be passed to the compiler, assembler, and linker. I have already those flags here defined. Feel free, of course, to use those flags for your own project. Now I need to define a Makefile variable to specify that those flags to be passed to the compiler. So I will name it cflags. Then plus equal, because here I am appending. Same here for this flag, and same here for this flag as well. Then for the linker, I have this set of flags, and I will need to create another Makefile variable to specify that those flags are for the linker. Our project doesn't contain an assembly files. Hence, there is no need basically to specify and use the assembly to process those assembly files, as we don't have them. So having the compiler and the linker is more than enough to compile our demo project. Now we can jump into our Makefile and start implementing basically the different rules here. First of all, we'll need to include the .mk file that we have created previously. So we're gonna include the tools.mk and then the toolchain.mk. This will define those global variables that are pointing to the top level directory where we are having the different tools and compiler. And this one is defining the content or the compiler to be used, the linker to be used, as well as the different compiler flags and linker flags. Then after that, we will need basically to create set of helpers, to be more precise, helpers, macros, and functions needed to create directories, remove or copy or whatsoever. For that, we'll need of course to use those Segwin64 applications to achieve those goals. I can create this function, create dir or create directory. This one will use the Segwin64 tools, and to be more precise, it will use the mkdir. Then we give -p, and then we give this variable or placeholder. So when we invoke this function, we'll need to give to this one kind of input parameter, and this input parameter will be referred by this $1. So this is the first input parameter to be given to our create dir or create directory. For the create directory, our parameter will be the path and the location where we want to create this directory. And of course, we want to specify as well the name of the directory to be created. So this full path that includes the path plus the name of the directory will be extended here, and we invoke this mkdir from Segwin to create our target directory. To copy file, we can create this template function, and again this one will invoke an application from Segwin64. Our application will be cp. Then we want, for instance, a recursive copy, and then our source from where we want to copy will be the first parameter to be given to this copy file, and the destination will be the second parameter. So we are copying a recursive way from 1 to 2. Now I had to add dash before the inclusion of those different .mk files. This is needed to properly include those files. Also, for our toolchain.mk, we are having or referring basically the location of the linker script, and this is part of our linker flags, as you can see. This is a Makefile variable that is not defined as part of this toolchain.mk, and by the way, this is the same for this build directory or build tier. This is Makefile variable that is pointing to the output build directory where we are supposed to have the outcome object files, final binary to be loaded to our hardware, as well as this map file that contains and embed useful informations like the location of the different functions, as well as the sizes of our data and BSS sections. We rely actually on our Makefile to define those variables. So before we include the toolchain.mk, we'll need basically to define those variables. So we copy here. This one will be the top level directory where our project is located. So if we go to our project, the linker is located here, this top level, then under the subdirectory, and here we go. So we go to our Makefile, and then we specify the subdirectory name. So when we are saying top level, this is relative to the location and the position of our Makefile. So this linker subdirectory has the same position as our Makefile. Now the build directory, this is the outcome directory where we should have our objects and final binary. This one should have the same position in respect to our Makefile. Hence, we can specify build only. We don't need, for instance, to specify like this or specify the absolute path. There is no need for that. Now, we have reserved the dependencies we had in our toolchain to the outside world, and to be more precise, to our color, which is the Makefile. We'll need now to create the list of sources to be compiled by our toolchain. So I will create this Makefile variable src, which is standing for sources. Then I will need to append each time the list of sources to be compiled. We need first of all to go back to our project and start looking for those .c files. Now the first .c files we have found is this helpers.c under common. Then we go to driver, and then under power we have a dedicated .c file, same thing for SPI, and finally same thing for OART. Here those are the headers, we don't compile them, this is the linker, same thing. And here we go, we have sources. Then we have another third location where we are having our .c files. So we need to code or encode basically those list of sources within this Makefile variable. So we're gonna use, if you remember this wildcard, to do the extension and expansion basically of the different sources. So the first location was this common. Then sources. So I go here, common, then src, then this one. So here I am expanding any file that is ending by this extension.c located under common src. I repeat the same pattern for the drivers. So I will have drivers, then power, then src, then .c, then same thing for SPI and same thing for UART. And finally, I will have the main source files under src. Now, after finalizing the steps, we'll have our src embedding all the lists of sources to be compiled by our toolchain. After creating our list of sources, we'll need to create the list of the objects out of those sources. What we need to keep in mind is that for each .c file, we'll have a generated .o file. Hence, we can create this list of the objects by doing the substitution of the .c by .o. Nevertheless, beside replacing the .c by the .o, we'll need as well to replace the path to the different sources by the path to our objects. The point is, after doing the compilation stage, we need to specify basically the build directory where those object file will be generated. And hence, most likely we need to place basically those objects under build directory. Therefore, those list of the objects must contain the paths to those objects directory. So let's start by implementing our list of objects. First of all, we need to create the directory where our object should be generated. So this we can rename it or name it as objects tier, and this should be located here under our build tier. Then option. Then we start by doing the first substitution, which is replacing the .c by .o. So we create our initial objects list, and then we invoke this expression to replace the .c by .o. This we have seen already. Here we are going through the list of the elements within our source list, and then we substitute any file ending with this suffix .c by .o. Then we can move to do the second replacement or substitution by replacing the path to the sources by the path to the objects. Here, as you can see, the different sources are not located within the same directory. So we have different paths pattern where our sources are located. Hence, we'll need first of all to create kind of list of those patterns, and then we iterate over the different paths and then substitute them by the objects directory. So this will be the first path to replace, then the second path, third, fourth, and here we go. We are done. Then we'll need to iterate over this list, and for each element we need to replace it by our object directory. For that, we'll invoke this for each loop, which is built-in expression within our make file that allow iterating over a list. This is quite similar to the for loop within a C or C++ language. So this is our iterator, and here we are iterating over the list of the paths pattern. Now what we'll need to do is to invoke another built-in expression, which is this eval. This eval allows the expansion of different makefile lists and variables within the context of our evaluation expression. So anything within this context will be expanded automatically. Then we'll need to create these objects again. This one will be updated on the fly. So for each iteration, we'll need to update our list of objects by the one that has already the path replaced with this objects directory. And then we need to invoke another expression, which is path subst. This one will try to substitute the path of our source by the path of our object directory. So this is the path of our source. As you can see, we are iterating over this list. Then of course we should point to matching expression, so we don't care here, and then this should be replaced like this. So we are keeping the same name of the file, and the only thing that we are doing is replacing the path, and this is done via this expression. And the evaluation is needed really to expand basically those Makefile variables as well as the objects. So the assignment must be done immediately. And the list, of course, will be our objects. So we need to go every time via this list, try to match basically this pattern. Once found, then we need to replace the path by this one. So every time we are updating our list by the element that has been matched within our for each loop. And here we go. So our expression is already ready to be tested. Now to inspect the outcome result from this for each loop, we can invoke this info built-in function to expand and display and print actually the content of our objects. This is kind of basic and trivial way basically to do debugging in our Makefile. And then we can just invoke make, and here we go. You see? So we are able to update the path to point to our object directory, and we are able as well to replace the .c by the .o. And here we go, this is our list of objects. Now we have finalized the creation of the list of the objects to be generated as outcome of the compilation stage. Nevertheless, the target of this Makefile is to generate the final binary to be loaded into our hardware device. This final binary is just the outcome of the linking stage of those objects. Now, the generation of the binary, as well as the generation and the creation of the different objects, will be done via a set of Makefile rules. So those Makefile rules are acting as functions that allow compiling the different sources to generate the different objects, as well as linking the different objects to generate the final image to be loaded into our hardware. Now, in terms of Makefile rules and goals, we need first of all to create what is called .funny goals. Those ones will be executed whenever basically we run make with this goal. So the make here doesn't rely if the file has changed or not. Actually, whenever it finds this Makefile rule, it will trigger the execution of the body of that Makefile rule. So our first target will be this all. And this will be our Makefile entry. And here we go. And this one will have a dependency to our final embedded system image to be loaded into our hardware. This means if we execute make all, then this one will wait that this file will be created before it gets executed. Therefore, we need to create another Makefile rule to satisfy what is called Makefile prerequisites that is needed by this funny target. Another useful Makefile target will be clean. We can use this one to clean up the build directory and remove it. And hence we can start over another build from scratch. This guy doesn't have to doesn't need to have a dependency. And here we will need to invoke segment64, then rm. And then we invoke this option. rm allow removing files and directories. And here we are saying please remove also files. So we are cleaning up the whole build directory. And what we want to clean up is the build directory, of course. So this .phony target will trigger the execution of our build flow, and this one will be used, of course, to clean up our build directory. We'll start by creating now the list of the Makefile rules to be able to generate the different objects and then the final elf. Now, right now, the final elf will be generated in the top level directory where our make is located. So we need to be more specific here, and we should put it within our build directory, something like this. The first Makefile rule will be the one used to create this program.elf, and hence we are satisfying this Makefile prerequisites, which is the dependencies to our .phony all. Now this one will have a dependencies, of course, to our list of objects. So this .elf is just the outcome of the linking of the different objects. Hence, we need to have, of course, the list of the objects generated to be able to link our program. Now, what this Makefile rule will do, first of all, we need to create a directory. And to be more precise, we need to create the build directory. For that, we need to invoke this Makefile function that we have created here. The build directory is not created by itself, and without a build directory, of course, the compiler will and the linker as well will not be able to place the different objects and linkers, and hence we end up by let's say crashes. So we need to satisfy basically this condition, which is the creation of our build directory. So this function will accept, as you can see, a single element, which is the path and the name of our build directory. In this case, will be build tier. Done. Now, the second line, of course, will be the invocation of our linker to link the different objects. So this is the Makefile variable that encapsulate the path to our linker. Then those are our linker flags. Those are already defined within our toolchain.mk. Then beside the linker flags, we need to specify the list of the objects. This is the main input to our linker to generate the .elf. To make things easy, we have seen that Makefile provide set of magic, let's say, syntax to reference basically those inputs and outputs. Here we need to use this syntax, or magic syntax actually, which is referencing all inputs provided as dependencies or prerequisites to our Makefile rule. Then we'll have an output, and this is basically will be our program.elf. We can reference the Makefile rule using this syntax. And we are done. We'll need then to create the different Makefile rules to generate the different objects file. So what we need to keep in mind, and I have been already insisting on it, is that each .c file will have a corresponding .o file. and not all .c files are located within the same directory. As you can see, we have a different, let's say, path patterns to specify the location of our .c. Hence, for every C path pattern, we'll create a dedicated Makefile rule. So our target will be, of course, the .o file. This will be located here under objects tier, and this one has dependencies to the .c file. So the first pattern is to generate the .o out of the .c of our common directory. So we go here and .c. Now the body of this Makefile rule will be, first of all, the creation of the build directory, and to be more precise, the creation of our build objects directory. After that, we'll need to invoke the compiler, then the compiler flags. Both of those are defined within our toolchain.mk. Then the input file. Here we have single input, let's say, pattern to be used as a dependency to our Makefile rule. Hence, this magic syntax is referencing the first element and unique element of our Makefile rule. -o, and then this destination pattern. We'll need to repeat this Makefile rule over different source directories. So this is for drivers, then power, then this is for drivers, then SPI, then this is for drivers, then UART. And finally, we have the main source directory, and that's it. Now this dependency will be resolved thanks to those Makefile rules, which will compile the different .c to generate the different objects that will create this list. Then this list will be linked to generate our program.elf. Now to test this, we can invoke the make clean to clean the build directory. Here we go, this has been cleaned. Then make all to build our project. And here we go. If we inspect basically our project, which is located here, then build. This is the program.elf, and this is the list of the objects, as you can see.